All right, so here we are recording, and what I've decided is that due to a whole bunch of things going on, both related to the class and not, today will be the last formal meeting of the class, where we're actually all here in this room. So I have one more thing to present, another Python example. So we'll go for that. We'll certainly have time for questions that anyone has on the remaining assignments. I think about half the class has turned in assignment 2. I will work on getting those graded pretty soon. At least it's pretty easy to do. And then next week, barring something unusual happening, I expect I will be here, and especially during this class meeting time, I'll be like in my office. So, so if you want, you can come by for help with any of the remaining assignments, or of course you can email me. There are certain things that I'd hope to present, but I was having technical difficulties getting things to work out, and so it just would not have gone well in class, unfortunately. But I figure everybody still has a good amount of work to do, so let's just and summer classes end next week anyway. That's the last week, so we'll just wind things down in an orderly fashion. So what I'll do is I will step through this example. And then I'll throw it open to any questions on the assignments. All right. So what I'm going to show you today, I'm going to save this file here. All right. Is going to solve the initial boundary value problem, or IBVP, and it's going to be a rather simple one, the heat equation. So UT equals UXX. I'm going to add a term to this to the right side, Q of X times U. So that is a reaction term. So this PDE is a reaction-diffusion equation. So the term that's involving just U by itself, no derivatives, that's a reaction term. The UXX is the diffusion term. Okay. And then on the interval 0 to 2 pi, of course for t positive, I'm going to fill in, I guess make something up for Q of X. Now, for this to be a well-posed problem, it is very important that the function Q of X be non-positive. So I'll just make a negative function here. So it is allowed to equal 0. It just can't be greater than 0. So 1 plus 1/2 cosine x and the negative of the whole thing, with cosine being between -1 and 1, it's guaranteed to be negative throughout. And initial condition, let's make something up. U of x0 is equal to fx, which I'll define to be sine x, let's say, plus sine 3x. Okay, and then keep it simple, periodic boundary conditions. Okay, so U of 0t is equal to U of 2 pi t. Okay. Now, and what I'm going to do is use finite differences for spatial discritization. So UT equals LU gets transformed into, so that PDE gets transformed in a system of ODEs. U prime of t is equal to a u of t, or is it equals in between there? U of 0 is equal to some vector f that represents the initial data here. Where L is the spatial differential operator that's described here. So I'll just fill in LU there so we see what L is. Okay. So I need a certain number of grid points for my spatial discretization. So I'm going to focus on spatial discretization first. Once I have my system of ODEs, U prime equals AU, I will need to do time stepping. I will come to that later. Okay. So, for now I'll just fill in, I'll make up a number of grid points, so like 128. And then, okay. And then my, okay, so this is number of grid points. And then I need a grid spacing, delta x. So that's just going to be length of my interval over n. Keep in mind for periodic boundary conditions, use all interior points and one boundary point, one or the other. I've seen it used where we include the left boundary point as unknown, but not the right, or vice versa, just not both. By contrast, Dirichlet boundary conditions, where you specify the solution on the boundary, use only interior points. For Neumann boundary conditions, where you specify the value of the first partial derivative, like a normal derivative on the boundary, I've seen different conventions there. Use all points, both interior or boundary, or I've also seen use midpoints of your. So you divide your domain into intervals of equal width, and then you choose your unknowns to be the midpoints of those intervals. So that seems to work well too. Okay, all right, but the first choice is what we're using, since we're sticking with periodic. But in case you wanted to take what I do here and adapt it to something else, this is how you could do it. Okay, now, all right. So now I need vector of x values. So for that, I will use my spacing times, I need to finally import something, numpy, as usual. Oh, whoops. Pi, I need math.pi. So I need to import math also. I have to make sure to stick more closely to my notes here. Okay, so I'll use an A range. So this will give me all the indices from 0 up to n minus 1, and then multiply that by the spacing, so that'll give me x equals 0, x equals dx, 2x, 2dx, and so forth, multiples of dx, up to and not including the right boundary point. So that's what I want. Okay, so on the interval 0 to 2 pi, again, a parenthesis indicating that 2 pi itself is not included. Okay. All right. Now, I need to be able to, I need vectors, values of my coefficient q of x, also my initial data f of x. So for that, I'm going to take math functions and vectorize them. Okay, so what I'll do is I'll make a function called This is getting aggravating. Because I indented this so much, it throws off indentation down below. Okay. All right. So I'll make a function called v-sign, and all that is a vectorized version of the standard math sine function. So then I can call v-sign of some vector to apply the sine function to every element of that vector. I'll do the same thing with cosine. Okay. All right. So now I can define my I can value my functions q of x and f of x on the grid. So that would be q is minus 1 plus 1/2 times v cos of x. Got to use the vectorized version or it'll be an error. And then same thing for f. So that would be v sine x plus v sine 3 times x. Okay, so now I have all of those. And I like to plot the initial condition. Because once I'm computing a solution, I want to plot it after every time step. But so that means I need to import plotting package. Wow, typed out all this much, I haven't even really done anything yet. Okay, so now I'll do plt dot plots. And I want to plot the values of f against x. And okay. Yeah. Let's see. Well, yeah, this code is runnable. Okay, that's so this is what my initial data looks like. It's kind of freaky, actually, because of overlaying sine x with sine 3x. It gives us this oscillation in here. Okay, so we're making progress on getting our system ODEs. We have like the initial vector, f. We have our grid, but now we need a matrix. So in the system ODEs, I need to define this matrix A based on the differential operator, second derivative plus multiplying u by q of x. So what I'll do is I need the standard difference for the second derivative. So I need a sparse matrix. So I need to import something else. So import scipy.sparse as sp. There's one more import I'll need. scipy.linalg. I'll call that SL. Although right now I'm not remembering exactly where I used that. Or do I really need it? Oh, yes, but later. Okay. So this is something that we've seen before, computing a sparse matrix for standard derivatives, so standard difference for second derivatives. I'll call it D2 as my matrix. So 1 over dx squared times, and I'll use sp.diags to make the matrix. And we've done this before, so there'll be 1, minus 2, and 1 along the diagonal. So and then we minus 1, 0, 1. So this says 1's on the subdiagonal, which is diagonal minus 1, minus 2's in the main diagonal, and then 1's on the first diagonal, that's the super diagonal. This needs to be an n by n matrix. So we put a shape n by n there. And then I'm about to modify entries, so I'm not going to use the default format for this. I'll use a usual CSR, compressed sparse row format. And of course, we're multiplying by 1 over dx squared. Now, I need to enforce the periodic boundary conditions. That means we need a circulant matrix. That means I need to take, like, the super and subdiagonal need to wrap around. That means I'm going to have 1 over dx squareds in the opposite corners of a matrix. So I have, like, in the first row, last element, so that's the index minus 1, it says last element is 1 over dx squared. And similarly, last row, first column is equal to that. So the first one of these is subdiagonal wraparound, and the other is the superdiagonal wraparound. So this gives us a n by n circulant matrix. Okay. Now, finally, I can make my matrix A. So that's going to be D2 for the diffusion part. And then I need a diagonal matrix that has the elements, that has the entries of elements as vector Q on the main diagonal. So that works out in a similar way. I'll have sp.diags, and my entries come from Q on the main diagonal, and only the main diagonal, also n by n. In my notes I put the format. I probably don't need to because I'm not really changing any entries, but just for consistency I'll put it in that format anyway. It would have to convert anyway just to add these two. So, okay. So now we have our matrix A for our system of ODEs. Are there any questions up to this point as to how we're getting this matrix? Or do we need to scroll up for anything?
The boundary conditions,
Yeah.
are you taking them from this graph?
Am I what?
Are you taking the boundary points from this?
Okay, well, this has to do with the fact that I'm using periodic boundary conditions, regardless of what this is. Because when approximating a second derivative, like at the first point or the last point, I need to use points that are outside of my grid points. So how do I get those values? I wrap around. Yeah. So that's what this does. Okay.
Dr. Lambert,
Yeah.
Question.
Yeah.
Why CSR as opposed to another form?
Well, there are many choices. Because the reason I use any format at all is if I don't put this format here, it'll use diagonal format, which is good for topos matrices like this one, but then it won't let me do this.
Okay.
Yeah, I found CSR or similarly CSC to be very flexible in terms of basically messing with the matrix.
But COO and other formats just...
Actually, no. COO, even though it's at the default format in MATLAB, not subscriptable. So for these purposes, any subscriptable format will do. Now, if we had Dirichlet boundary conditions where we would not need these corner elements, then I probably wouldn't specify a format at all. Because certainly, most cases we trust its judgment. Okay. All right. So now that we have the matrix A, we can actually. Any other questions before I continue? All right. So how are we going to handle time stepping? Now we've seen some time stepping methods, the simplest ones already, like forward Euler, backward Euler, Frank-Nicolson, etc. But now I thought I'd do something a lot more interesting. So for time stepping method, use a third order KSS method, which some of you deal with for your research or have dealt with at one time or another. So I thought this would be a little more interesting, even if more difficult to digest. But it's ideally suited for this kind of problem, where we have these periodic boundary conditions. And the reason why is, well, actually, first I'm going to put a framework in here. I'm going to set my time to be 0. I'm going to make up a final time, let's say 1. And if I need a time step, I'll just, the dt or delta t, I'll just pick 0.1. I need a number of time steps, which would be the time span divided by the time step. So that's how many steps I'll be taking. And then I'll use little n to index my time steps. So in this loop is where I have to fill everything in. So I need to do some initializing. Okay, I'm going to set u equal to, I'm going to make a copy of f, just so that f doesn't get accidentally overwritten. So u is my solution at the outset, and it'll be updated. So in this loop, we need to update u. Once that's done, I'm going to want to, well, actually, I'll call my new solution u new, and then I will copy u new into u to set up the next time step. I'm using a separate variable because well, I'm going to be referring to u throughout. I don't want to override it until I'm completely done. I'll want to plot the solution that I've just computed. Whoops. That's plot, not show. Show goes down here. I want to update time by adding dt to it. And I'll also want to pause after every time step. And actually, I want to do that up here also after I plot the initial data. Okay. So right now, I have everything except this big gaping hole of actually computing u new. All right, and that's where the KSS method comes into play. But right now we have like at least a framework here. Okay, actually for initializing purposes, I'm going to make u new as a 0 vector that's the same size as u. So because what I'm going to do is I'm going to keep adding on to u new to get the solution at the new time. Okay, so in here is where the magic happens of computing the new solution. But before I actually fill in any more code, I want to show you mathematically what's going on here. Okay. And we'll just build this one piece at a time. Okay, now here's our key right here. Because we have a periodic boundary condition, your solution is going to be a 2 pi periodic function. A solution u of xt can be represented this way as a Fourier series, that like what you've seen in any introductory PDE class. So it's a linear combination of cosines and sines. Even here, when cosine of 0, which is 1, this is also a linear combination of, so this is included a linear combination of sines and cosines. Whereas in my code, capital N is the number of grid points. So because we're representing a solution in this form, then our unknowns actually become the AKs and the BKs, so these coefficients. So we just figure out how to compute those, then we're ready to go. So what that means is I'm going to have a loop I'll actually have a loop that goes from 0 up to n over 2 minus 1, and that'll compute all of these coefficients. So for k equals 0, I only will deal with cosine. And then for all other values of k, I'll deal with both cosine and sine. Now, so for that, I'm going to need an inner loop. So to handle the Fourier series, okay. First, a convenience, but it turned out to be absolutely necessary. I'm going to find a variable n2 to be n over 2 rounded. It turned out to be absolutely necessary to do this because if I just worked with n over 2, even though n is an even number, it would be represented as a floating point number, and to use it in a range, it has to be an integer. So force n over 2 to be an integer. So now in here, where I can start the time stepping part, I'll have a loop for w. Well, actually, no. I'll keep it consistent with what's in my notes, but I'm just showing you here. K in range n2. So in other words, k equals 0, 1, 2, up to n over 2 minus 1. Those are all the values that I want. Okay. Now, I need a colon here. Okay. And we see we have cosine terms and sine terms to handle. But sine will only come into play when k is strictly greater than 0. So if k is greater than 0, then we'll deal with that. But for all values of k under consideration, we'll deal with cosine. Okay. Now, if we go back to the Fourier series, I need to compute these coefficients and multiply them by the appropriate cosine or sine. And our solution is evaluated on the grid at our x values. So I need these cosines and sines at those x values. So I'll just go ahead and evaluate those. So I'll call this like ck is v cosine of k times x. And similarly for sine part, sk is equal to v sine k times x. Yeah. It's wait a minute. Okay, hang on. This document right here is not part of any assignment. Okay, I'm using it as a reference. This is actually from 685. So yeah, if you go to my 685 site, you'll find it there. Okay. Yeah. Okay. Yeah, if it's the only place where I have KSS written up in this form. Okay. All right. So once I compute these coefficients, the AKs and the BKs, I just multiply them by these and add them up. So so here I need to compute AK, which I'll have to come to in a bit. Similarly down here I have to compute BK. So if we already assume that we have it, then I would just add these on. So like my new solution is equal to itself plus AK times CK. So this adds on a cosine term. And similarly down here, BK times SK. So the only piece not filled in is how to actually compute AK and BK. In fact, yeah, that's what's warning me about right here. Undefined name, AK and BK, because I haven't done them yet. Okay. Now, one thing I want to point out before I continue is the way I'm writing its code is horribly inefficient. Here where I compute V cos and V sine, because not only is it happening for every value k in this loop, it's happening every single time step. It really should be computed once up front and then reused. But at the same time, though, if capital N is large, that's a lot of storage. Really, the better thing to do would be compute AK and BK. And, okay, so I'll make a note here. Compute all the coefficients, AK, BK, then perform inverse FFT. Although that's going to create more complexities because I not only need CK and SK for this purpose of summing these terms up to get the solution, but in terms of computing the coefficients AK and BK, I also need them for that. So right now, there's no getting around creating these vectors. I wouldn't necessarily have to create them in this loop. Again, like I said, they should be done before this time-stepping loop. But also in terms of what else follows, like computing AK and BK, there's also inefficiencies there. But right now, we're just aiming for accuracy. Optimization is something that can always happen later. In fact, it's better to make it happen later. It was Donald Knuth, the professor of the art of computer programming, who I actually knew of. I met him when I was at Stanford. He said, premature optimization is the root of all evil. And I've found it to be absolutely true. Go out of your way too early to make something more efficient, especially what if you damage correctness, and it's hard to go back. Because also, more efficient code is harder to understand, especially for someone else who didn't write it. Okay, so how to compute these coefficients. So that is described over here. Now, so here are the formulas for AK and BK. But I want to take a little time. It's not really worked out in here why these formulas are the correct ones. Okay. Okay, as far as where to do that. Okay. Okay, so I'm going to, in some form, reproduce the Fourier series that's in that other document. Now, the coefficients AK and BK all depend on T. Just for convenience, I'm not explicitly indicating that dependence here. But we can think of T as being some fixed value. Now, the formulas come from these essential properties. First, the solution is equal to e to the LT times f of x. So if you take your spatial differential operator that can be exponentiated, it's well defined for operator periodic boundary conditions. That operator applied to f of x gives you the solution. Now for our system of ODEs, that translates into the following. U of t is equal to e to the AT, where A is the matrix we created earlier, times f. So this is what we're after, at least approximately. So that's one thing that we use. The other thing is that the functions cosine kx, sine kx, where k is an integer, are orthogonal on the interval 0 to 2 pi. So what that means is that the integral from 0, I'll use like a LaTeX notation kind of here, the integral from 0 to 2 pi of cosine mx cosine nx dx is equal to 0 when m and n are not equal. Similarly, if I put a cosine with a sine, whether m and n are equal or not, or a sine of a sine with m and n not equal, that also will equal 0. So that orthogonality allows us to compute these coefficients much more easily because they're basically decoupled from one another. It's like when you have a system of equations, but all the equations get separated from one another. So you can solve each one like using a simple division. That's literally what's happening in this case. So here's what I'll do. My solution is, okay, so given my solution at a certain time tn, which I'll refer to as un, which I have in the document. Yeah, un. So that's the solution at the current time, and we want the solution at the new time, un plus 1. Okay. So what I'll do is, keep in mind that un plus 1 is equal to e to the a delta t times un. So that's our starting point. So now what I can do is use the fact that cosines and sines are orthogonal in both discrete and continuous sense. So here's the orthogonality in a continuous sense. I take these cosines and sines, or cosines and or sines, multiply them, integrate them from 0 to 2 pi, and I get 0. But if you're using a grid of equally spaced points, that orthogonality also holds in a discrete sense. So for instance, ck transpose cj is equal to 0 if j is not equal to k. So these are just ordinary dot products of these functions evaluated at the grid points. So that helps too. So if I represent un plus 1 as coefficient a0 plus a sum over k of ak ck plus bk sk. So the ak's and bk's are my unknown coefficients, and the ck and sk are the vectors I created down here, evaluating cosine and sine on the grid. But this is equal to, for my solution, is equal to e to the a delta t times un. So I have this to work with. So now I'll take a dot product with, for example, Cj for some j. So now what I get is Cj transpose e to the a delta t times un. So that's this left side taking a dot product of Cj is equal to okay, A0 Cj transpose C0. C0 is an implied vector of all ones. So A0 is a number, but really it's A0 times a vector of all ones. Plus the sum, AK Cj transpose Ck, plus, need to make this a little bigger, Bk Cj transpose Sk. And I'm going to make an assumption here, just for convenience. Assume that j is non-zero. Now, Cj, therefore, is orthogonal to C0. It's also orthogonal to all of the sign vectors. Any cosines are orthogonal to all the signs. So, I can simplify this quite a bit. So this term would go away. And this would go away too. But also, Cj is orthogonal to all of the Ck's as well, except for Cj itself. So what we get is this sum collapses into one term, Aj Cj transpose Cj. So now all I have to do is solve this equation for Aj. So it's what we have here in the left side, Cj transpose e to the at un divided by Cj transpose Cj. So that's it. That's your formula for your coefficient. And similarly, for Bj, is Sj transpose e to the at un over Sj transpose Sj. Any questions about all that? Yeah.
The e to the at, we have e to the adt. Is that?
Oh, that's dt. Yeah.
Okay. Just thinking I was missing stuff here.
Oh, yeah. Okay. Other questions? All right. And that's what we have here. The only reason in the formulas in this PDF that there's a minus is that my matrix A in this document is a negative of what I've been typing in the code. So it's really very consistent with one another, just a notation difference. So now these, now the idea is to compute these. But here's a problem. If we try to compute these exactly, that's prohibitively expensive. Once you get to even a matrix of a moderate size, MATLAB can churn on it for quite a while, and therefore Python would too. So we're not going to do that. But we don't need the whole matrix anyway. What are we doing? We're taking this matrix, multiplying it by a vector, and then taking an inner product of another vector. So it's kind of like one entry or selected entries, or n selected entries of this n by n matrix. So we use that to come up with a reasonably efficient way of approximating these quantities. So how to compute U transpose f of a v for generic U, v, f, and a. And for this discussion, I'm assuming that A is symmetric, positive, definite, which it is in this case, just to simplify things. So first thing that's done is I'm going to express. So here when we have U not equal to V, which we do in our case, that's called a bilinear form. I'm going to express this bilinear form in terms of two quadratic forms where you have the same vector on either side. So I can write this as U plus V transpose FA U plus V minus U minus V transpose FA U minus V all over 4. So now, so what that means is I can have two of these expressions where the vectors on either side are the same. So, so in other words, bilinear form as difference of two quadratic forms. So now we're at this problem, how to compute U transpose f of a U, or at least approximately. So what's done is we treat it as what's called a Riemann-Stieltjes integral, and we approximate by Gauss quadrature. So what's happening here do I have that in this document? Yeah. So this is what we're after. So this quadratic form, you can ignore the minus in our case, is treated this integral where the exponential becomes our integrand. And the measure alpha of lambda is defined in terms of the eigenvectors of A. The domain of the integral comes from the eigenvalues. A is the smallest eigenvalue, B is the largest. Okay. So, so the way we approximate this integral using Gauss quadrature, and it was actually my advisor, Gene Golub, who played a big role in developing this. Okay. And I won't be able to go through all of the details, but in terms of doing just enough to be able to code it, perform the Lanczos algorithm on A with initial vector U, and we'll perform a certain number of iterations. I'll call that K, capital K. So that's something that will have to be implemented. And then, all right, so that's the first step. Second step is, so the output is a K by K tridiagonal matrix, what I'll call capital T. The idea is A is a capital N by capital N matrix, but the matrix T much, much smaller. So instead of computing f of A, which is too expensive, we'll compute f of T. So in our case, that would be the exponential I'll show you how we can do that momentarily. And then what we do is our approximation is equal to U transpose U times our matrix F of t, and we take the 1, 1 entry of it. And that's it. That's your approximation. As for why it works that way, that's something I would refer you to Golub and Moran's papers about. Or, well, also, all of these resources are on my Math 685 site. A ton of work that's been done in this area, including some papers of mine. So, in terms of code, this is what we need to do to compute each of these coefficients, AK and BK. So I'm going to work from the top down here. So to compute AK, I need a function that will compute a bilinear form for me. So I'll write that function. Okay. Actually, I'm going to take this part right here. All of this is not directly related to, or can be separated from, the fact that we're solving a PDE. And I'm going to put all this up top. So I'll just paste those notes up here. So up here is where I'll deal with, and you can type it wherever you want if you're following along, but I can define some functions up here. That's why I'm putting this up top. So I need a function. I'll call it bilinear form, or bilin form, which we need a matrix A. We need vectors U and V. And for our case, we need delta t also, because that's a parameter in our function. So this is meant to approximate U transpose exponential of minus A, or not minus, A delta t times V. So that's this function's job. This part of a job, though, is very simple. I'm just going to use this formula up here. So if I also have a function whose job is to compute quadratic forms, so I need matrix A, vector U, and also dt, I can use quadratic form function to handle computing a bilinear form. So all it would be is compute a quadratic form with the matrix A, U plus V and dt, and again with U minus V dt, all over 4. So that function's done. One line. That's it. Now what about a quadratic form? Here I follow this procedure here. So I need a Lanczos function. That'll take a matrix A, and my initial vector I'm going to call R. I'll show you the Lanczos algorithm momentarily. And then a number of iterations K. So I'll fill that in a little bit. But once I have that, then I would call my Lanczos function with my matrix A, initial vector U, and then the number of iterations, I'm just going to use 2 iterations in this case. In general, the order of accuracy of time stepping is 2 capital K minus 1. So if I have K equal to 2, then I get third order accuracy, and that's what I want. Okay, so I go ahead and get my matrix T, and then I need to take its exponential. And for that, there's a function in scipy.linalg, scipy.linalg.expm. which does the same thing as MATLAB's EXPM. And I will call that on t times dt. So e to the capital T times delta t. And then all I got to do is take U transpose U. So I use NP dot U of itself times the 1, 1 entry of this matrix here, ET. And that function is done. So fortunately, these functions had very little to do. It's Lanczos where there's more work to be done. And I'll come to that in a little bit. But now I can call this function down below. So I can say that AK is equal to bilinear form with my matrix A, my vectors CW, CK and U, and my parameter DT, and then I'll divide that by, I have these inner products to divide by, so CK with itself. And also down here, matrix A, vectors SK and U dt over dot product of SK with itself. So it's these formulas down here that I'm using down here. So CJ or SJ corresponds to my vector U from the generic formulas. Here's my f of A. This is playing a role of my V, and then I have to divide by this inner product. Okay. So now, almost everything is in place, except for Lanczos. So any questions up to this point? I need to dig up the Lanczos algorithm, which I think is not in here. Okay. Oh, I can dig it up from here. Oh, unfortunately, it's split across 2 pages. That's terribly inconvenient. You know what? I'm not going to stand for that. I'm going to edit this document. Lecture2.tech. Okay. I'm going to put a page break in here. I'll show it. Okay. Okay, there's the algorithm. So not much to it, so that helps. From 685, yeah. What is posted on the web will still be split across 2 pages. Okay. So my initial vector coming in, that's what I'm calling R. Now here in this algorithm, the pseudocode, we have all these subscripts. I'm actually not going to use the subscripts because I don't have to store all of these things. The only thing that's missing from this algorithm is forming the matrix capital T, which, do I have it in here? I don't think I do. No, I don't. I think I might have that elsewhere. Let's check. Okay. I'm calling it J here. This is the matrix I need. I compute these. So what I need to do is compute these alphas and betas that you see here. Then put them in this matrix. Alphas go in a diagonal. Betas go in a super and subdiagonal. It's a symmetric tridiagonal matrix. Now, in our case, it'll only be a 2 by 2, but we're doing this as a general algorithm. So the algorithm here computes the alphas and betas. I still have to handle storing them in a matrix T. So I'll get this part in first, and then we'll deal with. Okay. I think what I'd like to do is, if possible, see if it'll let me close this altogether. I want to close everything. Okay. And then if I make this smaller, I want to have all this visible at the same time. Okay, good. All right, so this is what needs to be implemented. So R is the parameter, the input parameter coming in. Capital K is the number of iterations. Which is corresponding to little n over here. Okay, so what I'll do is I have R already. And I need to make a vector x that's a 0 vector, the same size as R. So I use numpy zeros like R. So now I have that 0 vector handy. And now I have a loop. So for however many iterations are specified, yeah, so this will correspond pretty much exactly to what you're seeing here. I need to compute a beta, and that is just the norm, the 2 norm of R. So that'll be np.linalg.norm of R. Okay, so that's the vector 2 norm. And then I need to keep track. Notice here I have xj and xj minus 1. So I have 2 x's to keep track of. In other words, I need to keep track of the current x and the previous x. Now here in the algorithm, it calls for computing x. So if I do that, x is equal to r over beta. But before I do this, I need to keep track of a previous x. So I'm going to save it. Old x equals x. Now, I have these 2 steps to perform, but notice here we have axj. Here again we have a times xj. If I type this exactly as it's written here, that's 2 matrix vector multiplications that are the same thing. That's wasteful. So I'll perform a matrix vector multiplication or a matvec up front. I'll make a variable called v, and it'll be a times x. And since A, I'm assuming, is a sparse matrix, which it is in this case, then I can do that star, as opposed to what happened in class the other day. All different ways of matrix multiplication, but at least here the star is okay. Now I can compute alpha. Alpha is equal to x transpose v. So that'd be alpha is, I'll use a dot product. And then I need to compute this r down here. So r is equal to, if I distribute ax minus alpha x, well, ax I already have, that's v, minus alpha times x, minus beta times old x. Okay, so now everything in this algorithm over here has been implemented. The only thing that's missing is, as I compute these alphas and betas, I need to store them in the matrix capital T. So I'm going to create T up front. Make a 0 matrix of size k by k. And then every time I compute an alpha, I'll put it on a diagonal. And then every time I compute a beta, except for the first one I ignore. But for all the other ones, I put on the super and subdiagonal. So in other words, if I'm going to ignore the first one, so I would need an if. If j is greater than 0, then I put beta on the, so the first line does the subdiagonal, and the second line does the super diagonal. So, okay. And once everything is finished, t is what I return. So now I have everything. So my Lanczos implementation is complete. And actually, I think I have everything now. Okay.
Dr. Lambert,
Yeah.
Question.
Yeah.
Is there going to be an issue with just calling beta instead of beta.copy?
Well, beta is a number.
Yes. Yeah.
Okay.
So it's.
Yeah. Okay. You have a question? "150 lines of code later." Okay. Now. Oh. Okay. Yeah. All right. I think I'm actually ready to run this thing. Well, now I actually need a console. Okay. So let's see what happens. Okay, that's the initial data. Notice it goes from like minus 1.5 to 1.5. Okay, thank God it appears to be working. So that's a warning from changing the sparsity structure at the very beginning. That warning shouldn't happen again. And what we see is that the solution is smoothing out. Also, if you look closely, it's kind of hard to see. On the vertical scale, it started out 1 plus or minus 1.5. Now it's 0.75, 0.6. It's diffusing, smoothing out, gradually decaying to 0. Slowly but surely. Okay. So if I maintain the same axis limits on all of these, then you'd really see that. Okay. Now, the last thing I want to do is I actually want to run this for different time steps to get an idea of the convergence as delta t goes to 0. Now, I don't have an exact solution handy. This is a variable coefficient PDE, for which you don't have formulas for exact solutions like you would in the constant coefficient case. But what I can do is if I compute this for a few different time steps and see how the solution changes, because for the smallest time step, that is closer to the exact solution. So the difference between successive solutions at like successively smaller time steps can still give you an indication of order of accuracy. So what I'll do is I'm going to take all this KSS stuff starting from here and package it into a function with parameters like capital N, capital T, and dt. But that means I'll have to indent all of this. So that's going to, well, fortunately, Python's editor caters to this quite well, the need to indent a whole lot of code. So at least it's a quick process. Or at least this particular Python editor does. I don't know if all of them do. Although I have to be careful. one that doesn't handle unindent properly. Okay. Actually, wait, that I need. Okay. Oh, and then once I'm finished, this is a function now. I need to return u. Okay. Now what I could do is I can compute solutions for different time values of delta t. Now, for what follows, I don't want to do all this plotting. I just want to compute the solution and be done with it. So I'm going to comment out the statements that like plot and wait for the user to hit a key and all that. All right, so now what I can do is the name of my file, KSS heat equation, and also the name of my function. Okay, so now what I can do is compute a few solutions. I'll use the same number of grid points, same final time, but I'll use smaller values of delta t. So like 0.1, I'll just keep cutting it in half. Okay. So the error estimate first time around would be okay. So if error first time around, oh, that's weird. Why does? Oh, I came across this before. Oh, I know why. I have to get rid of these statements. These, because I'm passing n, capital T, and dt as parameters, and then I'm properly overriding them. So I need to comment those out, where I set n, capital T, and dt. So now I got to do this again. I made the same mistake yesterday. Okay, so U1, U2. So all I was doing is computing a solution using the exact same parameters all 3 times, but not anymore. And I noticed that when I compute U2 and U3, it takes a little longer because it's taking more time steps. So now, if I compute the error, let's take a look at it. Pretty small, a near 10 to the minus 6, that's good. And then I compute another error estimate. Actually, I shouldn't do that. I'm going to compare everything to U3, because U3 is the most accurate solution. So I'm treating it kind of like an exact solution in a way. Okay. So now, look at error 1 and error 2. So it's decreasing. If I look at the ratio of the two, so for a third order accurate method, I would expect the error to decrease by a factor of 8. It actually did better than that in this case, so that's quite nice. That happens from time to time. But chances are, if I let delta t get smaller and smaller, then that ratio would get closer and closer to 8. Actually, out of morbid curiosity, if I compute one more solution at an even smaller time step, and sure enough, it's taking longer because it's taking more time steps. Okay, if I compute U2 minus U4, and then U3 minus U4, Okay, yeah, sure enough, a ratio really is getting closer to 8 for a third order accurate method. Okay, so this is how my research program started, in a way. This is what I was doing for my dissertation. Okay, and trying to establish why all this worked and try to prove some things about it. Okay, so so any questions on what happened here? Yes.
Can I look at the formation of matrix A? It's not working.
Okay. A. Whoops. Okay. Here.
Yes.
Okay.
Where do you put the defined
Where I put the what?
the turning this into a function.
Oh. Okay. So what I did was. Oh yeah. After bilinear form.
Okay. And you just commented out the.
Any place where I set these parameters, I had to comment out those statements.
Yes, okay.
Okay. Other questions about this, at least? All right, this is quite a mouthful. So I'll post this as usual. Do we have any questions about either assignments? Well, yeah, I think there's still a few more people who have yet to turn in the second one. So anyone got to start on the third one?
Well, I've got to start on mine.
Oh, true. Yeah, so you're doing. No. Okay. Well, there's still some time, little over a week, to get the third one done. But I won't be burdening you with anything else. Okay. So no one has questions on the homework.
The third one, are we performing 3D
A what?
analog? Are we performing a 3D analog of triangular domain? Is there a special? Triangular special domain?
I think we're talking about different things. Okay.
I was trying to
Okay.
get an idea of what you are supposed to do.
Now, okay. If I go to the file that I posted. Okay. Well, yeah, this file. Yeah, because this has everything you're supposed to do in here. Now, please make sure you're dealing with the correct version of a book. And I updated everyone with that version. The pronomalic exercise is the one to do. Apparently you were looking at this,
Yeah.
which was exercise 11 until I updated it. So, all right. So go back to your email. I actually want to check on that. Yeah, on July 3rd, I sent the. Yeah. Oh yeah, you're not doing any 3D triangulation in this. I didn't talk about finite elements at all. Okay. But yeah, the file that I posted on the assignments page, that's really your where everything's laid out. Okay, so but I will be around next week for any difficulties anyone has with that. So as far as any questions that anyone has now, going once, going twice. Okay. Well, there you have it then. So that brings the day to an end anyway.